want to take a minute just to describe and familiarize ourselves, and in some sense refamiliarize ourselves, I suppose, with notation. And this is going to be a notation that is going to be really helpful for us whenever we start to try to take the derivative of functions that result from composition, functions that result from two functions being chained together. And here's something, just a basic example here. If y equals x squared plus 5x, then one way to communicate that we're referring to the derivative is the notation dy over dx. So y equals x squared plus 5x, then the derivative is 2x plus 5. And in particular, the way that we've expressed the derivative here, dy over dx. Now, let's take a look at this equation, which may look kind of strange in comparison to what we standardly see with x and y. Maybe this has r and s, but so be it. R is equal to cosine s plus 7. Now you could take the derivative of this function, in particular the derivative of this function using s as your variable of interest, and if you did, the 7, like all constants, would drop off, and the derivative of the cosine would be negative sine. But now here's the question. What I'm looking for here is the way to express the derivative in this situation, because the derivative here is not the same as, you can't just write dy over dx because we're not dealing with y and x here. Well, if y equals this, or y equals something in terms of x yields dy over dx, then r in terms of s would be dr over ds. And this idea, I claim, is really valuable to us because if you think for a minute about these functions, like say sine e to the x, you almost or at least I think to myself, this function y equals sine e to the x, that's a very cool function. It resulted from composition. But if I want to take its derivative, man, I wish this function was just y equals sine of u. Because if it was just y equals sine of u, I know how that story plays out. If I have y equals sine of u, then I know the derivative is just cosine u. But I want to pause for a second because I don't just write dy over dx here, because at this point, taking the derivative of sine of u, I don't have the x variable anymore that I'm working with. I'm now working with the u variable. So if you think about this for a second, you say, okay, what is the derivative here going to be in terms of notation? Well, just like the standard derivative is dy over dx, in this case, it's going to be dy over du. I claim the same sort of idea of saying, man, this sine e to the x looks complicated, looks difficult, not sure how to take the derivative. I wish it was just sine u. If it was just sine u, I could totally take the derivative of that, no sweat, and no problem. Well, the same thing kind of applies to that function e to the power sine x. Because that looks tricky in terms of how to take the derivative of it. It's not a sum, it's not a difference, it's not a product, it's not a quotient. It's a composition of two functions chained together. But then you say for a second, if you just take a step back and say, man, I wish that sine x wasn't in the numerator, or wasn't in the exponent, because if this read just y equals sine e to the u, that is super easy to take the derivative of. I can totally take the derivative of that because I know the derivative of e to the u is e to the u. And then, well, let's think about what goes on the other side, because here we have y equals something in terms of u. So this is not dy over dx. No, this is dy over du. But the long story short is, as long as we keep track of our letters properly, I claim this is going to be of value to us as we sort of step forward into ultimately being able to take the derivative of functions such as this. Before we do that, though, I want to take a moment to give you some examples so that we can sort of tune our eyes to how composition manifests and how we can use this sort of u idea to our advantage.